Okay, here we're going to look at a dual cycle. It gives me my initial conditions, P1 and T1. It's a compression ratio of 16, cutoff ratio of 1.15, and then it tells me that there's a pressure increase of 2.2 during the constant volume heat addition, which is process 2 to 3. Okay, so the pressure here is 2.2 times bigger than the pressure here. Okay, and then it gives me the mass given there. So first off, I'm going to look up state 1. Okay, 1 to 2 is the isentropic compression, so I'm also going to look up VR1 because I'm going to use that volume ratio to figure out what's going on at state 2. So at 300 Kelvin, my U value is 214.07, and my VR value is 621.2. So go ahead and jot those down. So 214.07 and 621.2. Now, for the isentropic process that I have here, I am going to say that VR2 equals VR1, or VR2 over VR1 equals V2 over V1, which of course is 1 over R, which is 16. From that, I can calculate that VR2 equals 38.825. So VR2 equals 38.825. Now, for state 2, I need to look up U2, okay, because that's 2 to 3 is the constant volume heat addition. So I go to VR at 38. Okay, VR is 38. So I'm right in here, and I get a T value of 862 and a U value of 643.35. Okay, so that U value again is 643.35. T2 is 862.4. Okay. Going to state 3. State 3 is a constant volume heat addition. Okay. Since it's constant volume heat addition, what I know is that T3 over T2, because of the ideal gas model at a constant volume, equals P3 over P2. Again, I can think about it as RT over RT, the R's cancel. PV over PV, the V's cancel because they're constant, so I can use this relationship knowing T2, knowing that P3 over P2 is actually, that means, well, here's what it means. It means T3 is 2.2 times T2. That tells me that T3 equals 1897.3. Yep. So T3 equals 1897.3. Now, from this, I'm going to go ahead and look up both U3 and H3 because, again, this is the constant volume heat addition, so I need U to find that. And then this is the constant pressure heat addition, which I need H for. So I'm going to look up both of those values. So I go to approximately 1900 Kelvin, just below it. I'm right here, and I get a U value of 1580 and an H value of 2124 for that temperature. So U3 equals 1580. H3 equals 2124. That sets state 3. Okay. Now, going 3 to 4, that's the constant pressure heat addition. So the same idea I'm going to use down here where T4 over T3 equals V4 over V3. And of course, this right here is my cutoff ratio. So I use that cutoff ratio of 1.15. I know temperature 3. From that, I can calculate temperature 4. Temperature 4 then is 2182. From that temperature, I can then look up, I need my H value here, because again, 3 to 4 is my constant pressure heat addition. Okay, and then 4 to 5 is my isentropic, so I'm going to use VR4 to go from state 4 to state 5. So 2182, I get an H value of 2480, and I get a VR value of 2.0707. Okay, at that temperature. So H4 equals 2480.6, and VR4 is 2.0707. Okay, now going from 4 to 5, again, I'm going to go VR5 over VR4 equals V5 over V4, right? Because again, this is an isentropic process. Okay, well, V5 equals V1, so I switch that to a V1 because it's constant volume from 5 to 1. Okay, and then essentially I divide by V2, multiply by V2, and I get this. Okay, so again, that's because this is constant volume. I just multiply and divide by V2. Well, V1 over V2, this is my compression ratio R, right? Okay, V2 over V4, okay, that V2, so this actually equals R. V2 and V3 are the same, because that's the constant volume heat addition from 2 to 3. This guy right here is 1 over R, so it's, or by R I mean cutoff ratio. Okay, so I can figure out VR5 knowing the compression ratio and the cutoff ratio, okay, as shown right here. Okay, and that gives me VR5 equal to 28.81. Okay. From that, I'm going to look up U5, which is what I need to figure out the heat rejection. So I go, and it's 28.81. Okay, so it's right in here. I get a U value of 721.2. Now I've set all of my states, 1, 2, 3, 4, 5. Okay, my thermal efficiency, by definition for a dual cycle, okay, is, sorry, just let me, I want to make sure I get the equation right. It's going to be 1 minus, and then on the bottom it's U3 minus U2 plus H4 minus, these are the Q ins. Q out is U5 minus U1. So again, knowing all of my states here, I can easily calculate my thermal efficiency. And I find my thermal efficiency to be 60.8%. Okay. So again, this dual cycle is just a combination of the diesel and the Otto cycle, where I've got both a constant volume heat addition and a constant pressure heat addition. Okay, using similar relationships for isentropic processes, constant volume, constant pressure, ideal gas, I can set all of my states. Once I get those set, finding U and H values, I can easily calculate my thermal efficiency.